Good afternoon. My name is Chris, and today I'm going to talk about the Extreme Value Theorem, which is essentially a really fundamental theorem in calculus and real analysis. So those of you who've taken a class in calculus or real analysis probably most likely come across this theorem. So I'm just going to discuss it a little bit and then go over a really interesting proof of the theorem. So essentially, this theorem's about functions that are continuous on closed and bounded intervals. And it says that if you do have a function that's continuous on a closed and bounded interval, and if you let alpha be equal to the infimum of the function over that interval, and let beta be equal to the supremum of the function over that interval, then there exist points x1 and x2 in that interval such that the function actually assumes those values of the infimum and the supremum of the function. And if that kind of sounds really confusing, it's kind of easier to think about this in a picture. So basically, if we have a continuous function on a closed and bounded interval AB, which we have here, we're saying that the function, the extreme value theorem says that the function actually assumes these values of the infimum and supremum of the values of the function over this interval. So if you take all of the values of the function over this interval, which is this set right here, alpha, which is infimum, is the greatest lower bound, and beta, which is the supremum, is the least upper bound. We're saying that the function actually takes those values over this interval. And so I'm going to prove that it actually takes the value of the infimum. And the argument is similar for the case where it also takes a value of the supremum, but I'm not going to go over that in this video. But the argument's similar, and you should be able to kind of reason through it after seeing this. Okay. So the proof is by way of contradiction. So we're going to assume that there is no point x1 in the interval such that f of x1 equals alpha. Then it follows that for all x in the interval, the value of the function has to be greater than alpha, because since alpha is the greatest lower bound, it either has to be, all the values of the function have to be greater than or equal to alpha, but since we're assuming that they can't be equal, they all have to be greater than. So now we're going to suppose that we do have a point t in the interval. So we know that the value of the function at t is greater than alpha. And it's also true that we can also take the average of those 2 points, and that average point is in between those. So we have the average of those 2 points in between those 2 points. And also, since f is continuous at t, we know there exists an open interval it centered about t such that all the points in that open interval, the values of the function at those points exceed f of t plus alpha over 2 whenever x is in that interval. So whenever x is in that interval, we know that all the values of the function at those points exceed f of t plus alpha over 2, because we know f of t exceeds that point. So we know there exists a neighborhood around that such that all those points also exceed that value. Also, notice that the collection h of all those intervals for each point t in the interval AB, if you take the collection of those, they form an open cover of AB. And since AB is compact by the Heine-Borel theorem, there exists finitely many points t1, t2 through tn such that all those finite intervals cover AB. So basically, the Heine-Borel theorem says that every open cover has a finite subcover, and we're using that fact. So we know that there are finitely many I sub t intervals that cover AB. So in that case, since there are finitely many, we know there's a minimum. So let's let alpha 1 be equal to the minimum of all those fti plus alpha divided by 2, which is just all those averages. Then since AB is contained in the union of all those intervals, t being in AB implies that alpha 1 is less than the value of the function at t. And that's because we're using that fact from before. So if t is in AB, we know as t is in one of those I subintervals. So we know that f of t would be greater than f of t plus alpha over 2. And then since alpha 1 is the minimum of all those, we know f of t has to be greater than alpha 1, which is the minimum of all those. But recall that alpha is less than alpha 1 because so what we essentially did was we found a lower bound of the function that's greater than the greatest lower bound, which was alpha. Because we found that if t is an AB, then alpha 1 is less than all the values of the function. So by definition, alpha 1 is a lower bound. But we said that alpha was the greatest lower bound, but alpha 1 is greater than alpha. So we found a lower bound that's greater than the greatest lower bound, and that is a contradiction. And thus the assumption we made at the beginning of this proof is false, so there has to exist an x1 in AB such that f of x1 is equal to the infimum. And that's the end of this part of the proof. I guess for this proof to be complete, we would have to prove also the supremum case, but the argument is similar, and I might do that in a different video. Thanks.